Okay, so for the last course, we already know how to calculate the stress and strain and the deformation uh, when a component or part is subjected to the actual loading or a torsion, right? And today we're going to focus on the pure bending. Okay, we're going to focus on the pure bending. Okay, so suppose we have the beam AB, right, with its initial length is L naught. Okay, and the axis AB is the neutral axis. Okay, it's the neutral axis. Okay, and then we define the coordinates. Y is above the neutral axis. Of course, you can define it as a below. Okay, it's either way. Depends on you're gonna figure out the strength on the top surface or bottom surface. Okay, or you're gonna figure out the strength above the neutral axis or below that. Okay. Okay. So therefore, the strength for a beam is subjected to a pure bending equals to L minus L naught, that is the change of length, right? Divided by the original length. Okay, so this original length due to bending, which can be regarded as the radius of curvature times the theta. Okay, and this theta is very small, so we only concern it is the elastic deformation. Okay, elastic deformation. It's a really small angle. Therefore, we can say the L naught equals to what? Equals to the low times theta. Low is the radius of curvature. Okay. So what is the L? L is the length after bending. After bending. Okay, after bending. So if we want to just focus on the specific location at position Y or position somewhere Y1 here, here, or here, suppose here, right? So at this position, which is the distance Y from the neutral axis, right? From the neutral axis. Okay, the same thing we can say the L, the length L equals to the low minus Y times theta, right? Low times Y minus theta. Okay, suppose the Y is right here, it's right here at the top surface, right? Therefore, we can say the low minus Y, right? It's this length, low minus Y, right? Times theta equals to L and divided by the low times theta. Okay, is that clear? And then we can rearrange this equation to get the strength of the pure bending equals to minus Y over rho. Okay, minus Y over rho. Okay, and then we can just rearrange it as the Y over C times the maximum strength. In this case, as located at the top surface of the beam AB. And C is the distance from the neutral axis to the top surface or the bottom surface, depends on you're gonna work on the compression or tension. Okay. Okay, so if we multiply the Young's modulus at the both side, right, here and here, you get the next equation, right? And we already know from the Hooke's law, we know the Young's modulus times the strength equals to stress, right? Equals to Y over C times uh the maximum stress, right? The maximum stress. Okay, and then we can rearrange the equation the maximum stress, the maximum strain equals to the minus y max divided by the radius of curvature. Okay, in this case, the maximum strain located where the top surface is. Okay, so we say the C, right? Okay, and the radius of curvature equals to minus C over the maximum strain. Okay, minus strain. Okay. Okay, so this is a deformation of the deformation of the direction for bending and the shear. Okay, so you should recap the those from your mechanics materials books, right? Okay, so if we bend it like this way, and the shear force in this direction is positive. Otherwise, it's negative. Okay, otherwise it's negative shear or negative bending. Okay. Okay. Okay, so let's calculate the stress from the pure bending. Okay, the stress from the pure bending. So the beam AB is subjected to the pure bending, right? Like this way, this way. So the top surface is under compression and the bottom surface is under tension, right? Is that clear? Right? Okay, so if we cut through this beam AB to focus on its cross section, what we get. Okay, suppose this is neutral axis here, right? And A is neutral axis. And we can define the small element or say the infinitesimal element just above the neutral axis with the distance y. Okay, so it's the infinitesimal small element dA, right? So during the bending is in this direction, right? In this direction, right? There must a stress, there must a load applied to this small area, right? Okay. And this stress on this small area equals to dF divided by the dA, right? From the definition of the stress. Okay, and previously we already know the stress from the bending equals to Y over C times the maximum stress. Okay, you get it? Okay, so if we just look at this small element, the A, whose moment applied equals to Y, the distance from the neutral axis, right, times F. It should be close, but the force is perpendicular to the distance. Okay, therefore say the Y times the dF, and we take the integration with the whole area, right? The whole area. The whole area. Okay. The minus because it is under compression. Okay, it's under compression. Okay, it's under compression. Okay. Okay, so let's just keep going. And we replace the F in terms of the sigma times the A, the stress times the area. Okay, and then we replace the stress with this term by here, and we get this, the next equation. Okay, and we just rearrange this equation. We get the moment, right, equals to the minus sigma max divided by C times C y squared dA times the integration of the y squared dA. Okay, and then we define this term is the second moment of area, of the second moment of area. Okay, therefore the maximum stress equals to minus mc. C is the distance from the neutral axis, right? It's a c, right? mc over the moment of air, second moment of area. Okay. And then the normal stresses due to bending equals to my over I. If we want to focus on the top surface, we just replace the y with c. The distance from the neutral axis to the top surface. If we want to focus on the bottom surface, the stresses applied to the bottom surfaces, we just replace the y equals to the distance from the neutral axis to the bottom surface. Okay. And this stress distribution, we like in this way. Okay. So what we get, we can replace a different y value, right? For example, this location is y1. Here is y2. Here is y3. And the top surface is y equals to c, right? Okay, so it's the stress distribution, normal stress distribution above the neutral axis. Okay, the same thing we can work on the bottom surface. I mean, we can work on the component below the neutral axis, and we get the distribution, stress distribution below the neutral axis is tension. Okay, is tension. Okay. Okay, so let's recap a little bit about the second moment of the area. I equals to the integration of the y squared dA, right? So suppose we have uh the cross section and we pick up one small element whose area is dx dy. Okay, and this here is this neutral axis, right? And with the width of this cross section is h and the height is h. Okay, suppose we define the neutral axis is the center of the coordinates. Okay, therefore can take the double integration from the coordinates like this. Therefore can take the integration from 0 to b, right? From here to here. And we take the integration from minus half h to the plus half of h, right? Y squared times the dA is dx dy. And we do some math calculation, we get its second moment of area. Okay, second moment of area. You get it? Okay, so just recap a little bit about the second moment of area. So we can check the table. It's not quite difficult for the regular shape, regular cross-section shape. Okay, just check the table or any handbooks. That's fine. Okay. Okay, deflection. So when the beam is subjected to the pure bending, where's the maximum deflection is? Where's the maximum deflection is? So we already know its strength is defined as the minus y divided by the radius of curvature, and the radius of curvature equals to minus y divided by the strength. Okay, from the definition mathematically of the radius of curvature, which equals to this. Okay, 1 minus y prime square with the power of 32. Okay, it's a mathematical definition. It's a mathematical definition of the radius of a curvature. So here I'm not gonna work on the math work. So I wanted you to know from the mass definition of the radius of curvature. Okay. Okay. So this term we can ignore it because it's take the derivative of the y prime, the deflection. As I mentioned previously, it is the elastic deformation. Therefore, the deformation is very small. Okay, and after you just double it, and we can regard it as the zero. Okay. Therefore, we can just rewrite this to the next equation, right? So the minus y over h equals to y over y double prime. Okay. So from the Hooke's law, the strength equals to stress divided by Young's modulus, right? And just rearrange this. Right? Just replace the sigma. Use my over I here. Okay. And then finally, we just figure out the y double prime equals to the moment function of x divided by Young's modulus and the moment of the area, the second moment of area. Okay. And here, the y prime is the slope. As what I mentioned, it is small, right? Slope. So what does slope mean? Or what's the definition of slope for a beam subjected to bending? What's the slope? For example, if we look at the point A right here, right? So the beam is subject to some pure bending or some bending, some distributed load or central load. This beam will be bending, right? Will deform like this way, right? Okay. So the slope, sorry, let's see. So the slope means the tangent of this beam with the horizontal axis. Okay, this theta. It's the slope. It's the y prime. That is the y prime. Of course, we can just figure out the slope at different location here. Okay, so its slope should be 0. Here, slope like this. Here, slope should be like this. Okay. Okay, so this table you guys have to remember it. Okay, so what we got from the previous slide, we got the y double prime equals to m over ei, right? Here. Right, the same thing. Okay, the same thing. Okay. So if we take the integration and take the integration, what we get the y prime and the y. And what is y prime? I already mentioned previously, right? The y prime means the slope. The slope, the same thing. Okay. And what is y? Y is the deflection. Okay, y is the deflection. Okay, y is the deflection? Delta. Okay. So the first things we have to find out what is the y double prime is, and we take the integration, and we can figure out what is the slope is and what the deflection is. Okay. Okay, so the key point is how to find the moment. The moment can be found from shear and moment, right? Shear, from the shear, and we can find the moment. How to find how to find a shear force? It can be found from the distributed load, or we say the load intensity, or the central load. The different load applied to a beam or applied to a component, and those load can be point load or distributed load. Okay, and those load or forces produce the shear, and the shear, from the shear we can figure out what is the moment is. From where the moment is, we can figure out what is the y double prime is, and we take an integration, and take the integration, we get the deflection. Okay, we get a deflection. Okay. Okay, so this is what we define. Okay, the sign convention for the pure bending. For the minus, what I mentioned means compression. Okay, means compression. Okay. Okay. So next we're gonna focus on the okay. So what's the transform section should be, and where is the centroid of the beam or of the components? Okay, and what is the second moment of the area is, and how to apply to the parallel axis theory. Okay. Okay, so let's just recap a little bit about the maximum stress from the pure bending equals to MC over I. C is the distance from the neutral axis, right? And we can define Z parameter equals to I over C, okay, which is the section modulus, okay, which is section modulus. So we can rewrite this, the maximum stress equals to M over Z, M over Z. Okay, so for this bending, the compression applied to the parts above the neutral axis, right? Okay, so if we bend the composite materials, what's that mean? If the beam is combined by two material, 1 and 2, so what's its materials property is? The Young's modulus, right? So let's assume that the E1 is less than E2. That means the E2 is higher than E1, right? And we just assume this two component is bonded tightly. Okay, there's no any slides in between. It's bonded. Okay, very very tightly. Okay, cannot be delaminate. Will not be peeled off. Okay. Okay. So this is the neutral axis. It's a neutral axis right here. It's a neutral axis. Okay, so we can plot the figure of the strand in x direction versus y. Y is the distance above the neutral axis, above or below the neutral axis, right? Okay, and then if we just plot this figure of this normal stresses versus the y, they were two profile of the stress distribution, right? So for the bottom parts, which has the higher Young's modulus, right? Which is a higher Young's modulus, right? That's mean it has the higher, supposed to have the highest stresses distribution because from the Hooke's law, right? It's from the actual loading for the bending is equals to my over I, right? My over I. Okay, so because the differences of the Young's modulus, its stress distribution is different. Okay, so here is the higher stresses. At the top surface, we say it's the top surface of the materials two, right? And surface right here is the bottom surface of the materials one, right? So the top surface has the higher top surface of the materials two has the higher compression, right? The stress than that of the bottom surface of the materials one. Okay, so there are two stress distribution. One is like this, and the second one is like this, right? Right? Because we assume these two materials bonded tightly, it will not be slide or it will not be peeled off. Okay, therefore this strand epsilon x should be linear. Okay, should be linear. Okay, because it's bonded together. Okay, it's bonded tightly. Okay. Okay, so that's where we already described that for this two materials bonded together, we get its strength distribution versus the y and its stress distribution versus y, right? So here is the normal stresses of the materials two. Okay, of the materials two. Okay, and how to convert this plot to a linear relation, right? Because there's a Young's modulus difference in between right here. Therefore, it's discontinued. It's discontinued at this interface. So how to convert this situation into a linear relation? We have to convert these two materials into one material, into one material. Okay, into one material. How? How? We just change the width of the materials two. Okay, just increase the width times the vector of n with the initial width of the materials two. Okay, therefore this case and this case are the same. Okay, and then its strength distribution is still remain. Okay, still remain like this way, sorry. Okay, still remain. However, its normal stress distribution will become linear. Okay, will become linear. Okay, in this case, we have two stress distribution, right? Sigma 1 and sigma 2. Okay, in this case, we only have to take the one stress into account. And its distribution will become linear. Okay, will become linear. Okay, it's linear. Okay, so why not we modify the high? Can we modify the high? I mean, this is the real case with two materials and has the different Young's modulus. So can we just change the height of this second material? Can we do that? Why we have to just enlarge the width but not the height? Why? Why? Okay, so let's think of this way. If we enlarge the height of the second material, right? What's going to be changed? What's going to be changed? The neutral axis, right? The neutral axis we're going to change to the other location. We have the new neutral axis. And this new neutral axis will be outside of the real case. Okay, will be outside the real case. Okay, suppose we look at the y over the strand. The figure of the y the strand, the epsilon x versus y, right? It should be linear, right? It should be linear, right? It should be linear, and it should be its strength should be 0 at the neutral axis. Okay, and then suppose we modify, we just enlarge the height. What we get a new neutral axis, right? So we have the new neutral axis right here. At this point, the strength should be 0 because it's a neutral axis. From the definition, the 0 strength at the neutral axis, right? And this strength versus y will be like this. Should be like this, right? Will be like this way. However, it is not true. It is not true, right? It is not true. It should be like this. Because here is the rear neutral axis. Its strength should be 0 right here, right? And this strength is different. With the new neutral axis, we have the new strength, right? Therefore, if we just transfer the height, just modify the height, the maximal strength and the slope and the neutral axis will change. Okay, it's make nonsense for the real case. It's not true. Okay, it's not true. Okay. Okay, so in this case, suppose we look into the small element again, right here, the small element, the A, and there's under the bending, right? The bending, there's a small force applied to it. Okay, there's small force applied to it. Okay, as I mentioned, we have to enlarge, we have to modify the width, right? But not the height, right? How to define the parameter n? The n equals to the E2 divided by E1, right? And E2 is greater than E1. Okay, E2 is greater than E1. Okay, and the small force applied to the small area, okay, the small force equals to the stress times the area equals to the E2, okay, E2 times the epsilon, the strength, right? This is the stress, right? Times the A, and equals to minus y over the load, the radius of curvature, right? Here, the strength, right, due to bending equals to minus y divided by load. And E2 equals to the m times E1, right? We want to convert it, the whole composite, these two parts, right? Two materials into one materials. We need the vector of n, right? Here. Okay, so we get the E1 times the epsilon, the strand, times the m times the dA. Okay, so the m times dA, if we look into the cross section with the small area, it will be enlarged in this case, right? Originally, you have a small area, right? After times the vector of n, it will be enlarged in width, okay, in width. Okay, so in this case, the neutral axis is located at the same place. It will not change. Okay, the neutral axis is remain no matter now it's composite or a single material. Okay. Okay, so like this. Okay, so suppose we have this composite beam with the T shape is made of the steel plates. Okay, and for this body part, the bottom part is made by the arc timber, and the Young's modulus of the E of the steel is 200 GPa, and for this Young's modulus of the wood is 12.5 GPa. And what is the maximum stresses is? Okay, so can you plot the moment diagram or where's the neutral axis? And what's the angle at the free end of the C? Okay, so in this case, this cross section of this beam, Okay, so let's work on this a little bit. If you still remember. Okay, so first things we have to figure out where's the neutral axis is, Y bar. Okay, from the parallel axis theory to figure out what is the, sorry, or to figure out its neutral axis. Okay. Okay. So this is the dimension of the cross section of this beam. Okay. Okay, so for the top, for the for the plate, okay, and we have to look at the two different parts. One is the steel, and the other is the wood, right? Arc timber, okay, arc timber. So the steel has the higher modulus, right? Steel has the higher modulus. So what we should do, we should enlarge, right? We should enlarge the steel, right? The steel part. So we know the E steel is 200 GPa and the E wood is 12.5. So the N vector equals to 16. So that means the steel parts have to be enlarged in width. So from the top, remember it's the cross section. Okay, here's the cross section. Okay, cross section is 100 times 16, right? And this the center plate, steel plate, have to be enlarged. It's 10 will become 160. Okay, 160. Here. Okay, so now we have to figure out what is the neutral axis of this modified composite beam is, Y bar. Okay, so the Y bar equals from this numerator is A1 times Y1 Where's the A1? A1 is the top plate of the steel, right? Top plate of the steel. Okay. And what is the A2Y2? Where's A2Y2? What is A2 or Y2? Remember, it's whole timber. Okay, it's whole timber. Okay, therefore the A1 is the top plate. Its area is it's 10 times 1600, right? After times the vector n, right? And times the 80 is the Y1. The 80 is from the centroid of the bottom part to the center of the top plate. Okay, so this distance is 85, and its centroid, the center of the top plate is 5, right? So the 75 plus 5 equals 80. Okay, so 80. Okay, and A2 times Y2, A2 is the bottom part after multiplying the vector n. Okay, therefore the A2 equals to 37.5 plus the 160 plus the 37.5 times 150. Okay, the bottom surface, right? This area. Okay, and the Y2 equals to 0. Why? Because it's coincides with the the center of the bottom part. Okay, and also just divided by the total area A1 plus A2, right? A1 plus A2. And then we find its neutral axis is 25 millimeter above the center of the bottom, the bottom part. Okay, so the Y bar, the neutral axis equals 25. This here is the neutral axis, 25. Okay. And then we can use the parallel axis theory, right, to figure out what is the moment of inertia, the second moment of inertia, right? I1 plus A1 D1 square plus I2 plus A2 D2 square, right? For the I1, it's the rectangular cross section equals to 112 times BHQ plus BHD1 square, right? Okay, for the bottom part, it's still just a rectangular, right? So the same thing. And we can plug all those numbers, BH, right? D1, D2, A1. And we just do some math work. We get the second moment of inertia of this component being is 1.367 times 10 to minus 4. Okay, and the y is defined as the distance above or below the neutral axis to the top surface, bottom or top surface, right? And then we can use this equation to figure out what is the maximum stresses is, right? The maximum stresses is. Okay, so today's course we're gonna stop here. So if you have any questions, just please feel free to email me. Okay, to email me.